This video is part of our enterprise architecture, application architecture section with examples using Microsoft.NET Blazor, Azure, and Great Ideas Trellis Spark. And in this video, we're going to be looking at an overview of workflow components. So in this presentation, we're going to be giving you an overview of workflow components. And we're going to try and answer a few basic questions. We're going to start by looking at data-less service components and how are they different from the standard SOA-based services. We're then going to look at how do we go beyond microservice architecture to something that we would call nano-service architecture. We're then going to look at how do we build these nano-services, how do we call or invoke the nano-services, what are the advantages from a DevOps perspective, and how this impacts sustainability of your enterprise architecture over time. So what are data-less service components? Well, essentially, if you've already mastered the idea of service-oriented architecture and building standard services that encapsulate their own data, so for example, if I have a customer, it encapsulates the customer data. If I have a service for order, it encapsulates the order data. And if I have a service for invoice, it encapsulates the invoice data. Essentially, what we're saying is that a data-less service component is not going to encapsulate its underlying data. All of that data, the customer data, the order data, and the invoice data, will instead be moved into our data at rest generic service, and our customer service will only retain the workflow functionality required to process customer data. So if I want to do something with a customer, I will call my dataless customer service. That dataless customer service will go to a common data at rest repository to get the customer data, do whatever it needs to do with it, and then put it back in the data at rest repository. So the only real difference between what we're describing as a data-less service component and a service component that you would build from any other idea of using service-oriented architecture or microservices is that we're taking the data encapsulation out of the service and we're moving it into a data at rest storage location. Now, cool thing about this is we're going to want to make sure that all of our data-less service components are going to run within the context of a secure user session. So what that means is that the service, the customer service, in order to be able to access the customer data out of the data at rest service, needs to be executing within a context of a known user account. So we must have a user. It must be in a valid session so that when that customer service is called, we're going to pass that user context into the service, and the customer service will use that user context to go to the data at rest and say, can I have this customer information? And then all of the rules that would otherwise be applied, determining whether this user with this role is allowed to access this customer in this state under these business rules, is then applied by data at rest, and I will only get access to that data if I'm allowed to see it. So data-less, we take the data that was encapsulated, we move it into the data at rest service, and then any execution against that service will use the user context to retrieve the information it needs and process it and put it back. So this is really cool because what it means is that any service, ideally, all we need to provide it with is session information, a user key, and then the instance GUID of the record on which it needs to operate. So we can basically plug and play any number of services here. Okay, so we would have a standard set of parameters that we're going to provide to our services. And this means that it's easy then to extend and integrate new services into our user experience on demand without having to come up with complex service contracts and interfaces and then figure out how does this form call this service as opposed to this form calling this service. And the other nice thing is obviously if we just got essentially simple information like a user key, a session key, an instance key, that then can be moved hierarchically down the services if necessary. So this gives us a very easy and flexible interface to be able to call any type of service component to do any sort of manipulation against the data set. Now, one thing that we'll look at when we're looking at the implementation and calling examples later in this video is that one thing that we might want to do is put a lock on the record that we're actually trying to apply the workflow to. So for example, if I'm processing an order or processing an invoice, I don't want two people trying to process that invoice at the same time. I don't want effectively a user experience where a user can click on two different forms very quickly and submit the same request against the same invoice at the same time, and then the whole thing tangles itself up. So one thing that we're going to want our services to have the option of doing, if they need it, is to put a lock on the record to prevent the multiple concurrent update scenarios. Because we're focusing everything through a single data at rest service, and the data at rest service is implying all of our security and access checks, we can add a lock check to the instance we're going to operate on for that service to make sure that nobody else is doing something to that particular record that they shouldn't be. So this then gives us a really simple process for a data-less service component. We're going to get the latest version of the record from the data at rest. We're going to do the work we need to perform on that particular record to complete the action, and then we're just going to put the results straight back into data at rest. And if we lock the record on entry, then we'll unlock the record as we exit. Really, really simple. This is very basic, clean interface implementation design. So we said in the overview that we're going beyond what would be typically defined as a microservice architecture. We're talking about something called nano-service architecture. So why are we making this distinction? Well, microservices using the standard SOA models are still encapsulating the data they operate on. So our customer service has the customer data, our order service has the order data. And essentially, to make that work, to actually encapsulate and do something with the customer data, that customer service has now got a bunch of other functionality that's happening inside it. That customer service in some way has to control the access to the customer data. It has to be able to persist and retrieve the customer data from whatever data storage it's using. There's a bunch of functionality associated with the data that's encapsulated. And what this tends to mean is that if I'm building a customer service to encapsulate a set of customer data, that I'm going to be putting a bunch of operations on that customer service. I'm going to have essentially a single customer service with maybe 100, or even in some cases we've seen up to 1,000 operations on that service to do everything that you're able to do with customer. And then that customer service with that big interface has got some data that it's encapsulated, which is its own customer records, but it's then making calls to order services and invoice services and so on. And then we have complexity in the case of, well, okay, do we need to cache some of this order data? Do we need to have some sort of eventual consistency where we're working in the service within the customer, but we're making changes to knock-on services further down the hierarchy eventually? So the microservice architecture, because we've encapsulated the data, means that typically our services tend to be larger. So one thing that we're going to try and achieve with a nano-service approach is how do we break that down? How do we make this smaller and easier to deploy? So one thing we can look at is domain-driven design principles. Now, whole books have been written about domain-driven design, but essentially what a domain is what we describe as a block of functionality. So for example, if I want to go to human resources functionality, this is essentially a domain. And within this domain, I have a sequence of form definitions, concepts, ideas within the domain that I need to be able to express information about. And within my domain, I might have a concept called a worker. And then for that worker concept, I've got some sort of user experience in terms of tabs and rows and fields. And essentially, this data description is defining the domain of human resources. Now, within Great Ideas Trellis Spark, the idea is that we want to put all of the data in that domain inside our data at rest service area. And that will be our system of record for all HR information. And what we want to make sure is that there is no state of any kind in any of our data in action service components. So that means that worker records are never in a service. They're always in the data at rest. And to make this work efficiently, we also need to make sure that all of our data in action service components, so all of our workflow components, have direct access to data at rest. So what this means is that if I'm trying to process a complex workflow where I've got information from customer, order, invoice, some fulfillment, and I've got that scattered across 4, 10, 40 different services, and I'm trying to execute a request that means that I'm using the old microservice approach with encapsulated data in each of these services, then I've got some complex functionality that's going to interact with many of these services, update data in lots of these services. I'm dealing with caching issues. I'm dealing with eventual consistency issues. I've also introduced into dependencies, because if I've got some sort of caching of orders in customers, then what exactly am I caching as far as the order is concerned? So if, for example, the structure of the order data changes, does that impact the cache in the customer? So there's a lot of sort of like issues around when you're looking at a typical service-oriented architecture at microservice that immediately go away when we're looking at data agnostic services, because each of our data in action workflow components has immediate and direct access to every single record that's in our data at rest storage area. So if I've got an operation that needs to perform a complex workflow, I can initiate that operation. I can go immediately to my data at rest, do whatever I need to do for that workflow, interacting directly with data at rest without having to go down a chain of other services. So what this means is that we can build a highly efficient set of nanoscale service components. They can be a lot smaller than traditional microservices. They can have a flattened hierarchy so that they're immediately able to connect with and manipulate the data they need. And it means that I can ignore all of the caching and eventual consistency and all of the other issues that come out of a standard SOA microservice implementation. And it also means that I can now say, well, I don't need to implement a customer service with 100 or 1,000 operations. I could potentially, if I wanted to, just deploy one operation per workflow component. And I would have no loss of flexibility or efficiency because of that. I would just have one component. So I might have a component that says process orders of type A. And that component will go to data at rest, figure out what the order is. It's a type A order. It'll do whatever it needs to do, put the information back, job done. Somebody comes along 6 months later and says, I've now got an order of type B. I can leave my type A order alone because I've still got some of those to do. I can deploy a new nanoscale component for order type B and deploy that into the system. And now when I've got an order of type B, it's going to go to data at rest, do what it needs to do, and come back again. So the really cool thing about these nanoscale service components is you can make them very, very small. You don't have to have an interface contract where you have a customer, and because you've got a microservice with encapsulated data and hundreds of operations, none of that exists anymore. Each workflow component can be its own entity and be built and versioned and deployed and scaled as a single workflow component doing a single optimized function. Okay, so the next question then is, how do we build them? Okay, so first rule of enterprise architecture and efficient workflow is push the processing as close to the data as possible. Every time you have to take the data out of a database, transfer it across a server or a service boundary, do some work on it, transfer it to another service, do some work on it, and then start pushing it back through multiple layers, multiple servers, you've got a time penalty, you've got an efficiency problem. So ideally, you want to push as much of the workflow and logic into the database as possible. Keep that processing as close to the data as possible. The other thing you want to do is keep that service hierarchy as flat as possible. So if you watch some of the go-to conferences where they're talking about microservice architectures and problems with building microservices, a lot of the issues come down to the granularity of the service contracts. And this is the conversation we were having about a customer service with hundreds of operations encapsulating customer data, calling an orders service with hundreds of operations encapsulating order data, and so on. And essentially what happens is that if you're initiating an operation where there is a fan out, so one call to one service fans out to 10 second level services, fans out to 100 third level services, every time you're making a service call like that, you introduce a performance overhead. So what you want to be able to do is collapse your service hierarchy as flat as possible. And when you think about it, the whole point of the Data Agnostic Services and the whole point of the discussion we've had so far about component workflow is that we have flattened it to, I'm going to make a service call to customer service. Customer service is going to in-out to the data at rest service as much as it needs. And that's it. There is no underlying hierarchy. It's not fanning out to 10 different order services or 100 different fulfillment services. It's being processed as a single entity from a single service call within a single service boundary. Now, building these fine-grained components is great, but the other side that we discussed on the previous slide was the idea of using a common interface. So ideally, we just want to give it a user GUID, a session GUID, an instance GUID, and that's it, done. Right? All of the services work the same way, and they effectively become plug and play. So in this instance, what we mean by plug and play is that ideally we want to be able to call any workflow from any of our user experience or any other workflow. Okay, so we do want to be able to compose things potentially, but the idea being let's make these things as small as possible. Let's use a simple interface to call them, and then we can just add them as and where we need them. Now, in line with our earlier comments around when we build code, we're incurring cost. One thing that we want to try and do as we build out these services is we want to create generic functionality that can be configured with data. So what do we mean by that? So essentially, although we're going to create these fine-grained services, instead of building a bunch of logic into there, essentially is hard-coded, but tends to make them fairly inflexible, what we're going to be looking for is opportunities to build a generic service instead, such that we can configure how that service works by looking at some data from within the database. So an example of this may be, for example, sending out a message. So I've got a message, I need to send that to a number of different endpoints. And I don't even know what those endpoints are at this point, right? I know that I'm going to put this message on a queue. It will have a subject, it will have a body. Maybe if it's an email, it will have a destination, sender and recipient email addresses. Maybe not. So ideally what I want is a generic service to send an outbound communication. And what I want to be able to do is when I call that generic service, I want to be able to read the configuration data from the database and say, this message is going to a service bus. And the recipient is not an email address. The recipient is a service bus topic ID. And here is the configuration information for that service bus. Here is how we're securing the service bus. And all of that configuration data is held within the generic service. So I have a generic service which enables me to send an outbound message. And then here is the message data I want to send. Here is a link to the configuration data that tells me how that service is going to work. And now I can use that service anywhere in my environment to send any sort of message to any sort of destination. So when we're talking about generic services and configuration with data, that's the sort of idea we're looking for, right? These utility services, what we want to be able to do is configure how that particular service is going to work in data, either as part of like a web config or a settings file when we're installing the service, or as part of the data set it's going to read as it starts up. So it will read its configuration data from data at rest maybe. So the idea is let's build as few generic services as possible. Let's design those from the start so that if there are any options as regards the implementation of that service, we do it through configuration data rather than through hard coding logic into the application. Now, another thing that we're promoting very much is the idea of reuse. Right? So I don't want to code the same bunch of code 15 different times. I want to code it just the once. So one thing that we are focusing on as part of our enterprise architecture as design principles is building reusable class libraries. So the objective when we're building our nano-services is to put as much of the logic into a reusable class library as possible. Okay, so these reusable class libraries typically are then easier to build and test, right? They're just a class library. They are a standalone thing that I can design, I can build it, I can test it, I can put some automated tests around it. Whenever I make a change, I can put it into a DevOps release pipeline so that the change triggers a build, triggers an automated test run, gives me a result set, did it work, right? So using a class library is always good, and encapsulating as much of the logic into the class library is even better. Now, the other really cool thing is obviously we can now reuse that class library across multiple services, and that's good because what this means is that instead of in a microservice environment where customer service calls, order service calls, invoice service, every communication that crosses one of those service boundaries is doing some sort of inter-process communication. And if those services are resident on different servers, perhaps behind load balancers, and you've got network crossing to consider as well, then every time you make a call, then you've got an overhead in terms of marshalling the data, actually passing the data to the target. It then needs to be taken from the data stream in the target, decoded for the target. It needs to do its operation. It then needs to marshal and encode the reply. It needs to go back over the communication mechanism and then be sucked into the service. So even if you're using some sort of real-time communication fabric, that buffering of data between the processes, even if it's on the same server, can be time consuming. If you're actually passing data through REST APIs, that can be extremely time consuming and put a very high latency on the overall communication. So a really cool advantage of using a reusable class library is that that can be reused within the compilation of the nano service. So essentially you've got one call into that service component and then everything is executing inside that service thread. Right, so even if you have a thread within a process, you're not going in and out of the thread to do different things. Right? All of that communication and logic is essentially encapsulated within that thread. So that makes that efficient and really boost the performance. And then the only time we're actually crossing a service boundary is where I'm going to go and find data that I need to operate on, or I'm going to be writing my results back. So essentially that gives us, by architectural design, the most optimum performance solution. So we've got these nano services. This seems to be a really good idea. And the question then comes is, what technologies do we use to build them? Is there any limits? And the answer is, in practice, yes and no. Essentially, we can use anything that you can invoke and connect to data at rest. So absolutely anything on this list: databases, server-based APIs, web APIs, operating system services, cloud services, anything can be used to invoke workflow automation as long as we can connect it to data at rest. So that seems to be everything. In practice, limit yourself. Every time you use a different technology, you need different expertise to manage and maintain it. If you've got half your infrastructure working on PHP, half your infrastructure working on a Microsoft stack, then half your developers are supporting PHP LAMP stack, half your developers are supporting Microsoft stack. And if there's an urgent need to move PHP developers onto your Azure stack or vice versa, you've got training issues, you've got flexibility issues. It's not good, right? So one thing that you want to try and do when you're considering which technologies you're going to use in your architecture is come up with a reasonable minimal set. So that's not to say only use Microsoft, only use LAMP, only use WebSphere or whatever, right? You might have a mixture of technologies in your stack in your enterprise anyway, but come up with what is a consolidated list. What makes sense? How few can we get this down to? Because the fewer different technologies you use, the easier it is to make sure that all of your developers are cross-trained across multiple different services, across multiple different technologies, the easier and more flexible it is to be able to move development effort from one project to another. So although nano-service architecture you can implement using anything you want, we do strongly recommend that within your enterprise architecture, you set some guidelines and constraints around what your teams are actually allowed to use. And then if a new technology comes along, then great, modify the enterprise architecture, set new standards, make sure that people are using it properly. But don't let people just go off and use whatever they decide to use because they just saw a really great YouTube video that said, you know what, this PHP technology is the latest and it's really great and we should all be using these libraries going forward, because so much of that just falls by the wayside, 2 years, 3 years, 5 years later, and then nobody's supporting it, nobody knows about it, and it was nice at the time, but it's not going to last you for 15 years. So keep a focus in your enterprise architecture, focus it down onto a set of technologies that you're going to maintain and work with long term. Update that list by all means as the technologies change and evolve, but make sure it's a part of your architecture. What are we doing? Why are we doing it? How are we using it? So as we said on a previous slide, one of the things that we really want to do here when we're building out these sorts of solutions is we want to put as much of the workflow processing as close to the data as we can. So this is why databases is at the top of this list. So one thing you really want to be focused on as enterprise architects as you're building out your dev team is make sure that you've got some people who are skilled at writing stored procedures and triggers in whatever languages and databases you actually choose to use. So this is a really good investment that a lot of people fail to make. Okay, so a lot of workflow automation is generally done, in business objects that are essentially very close to the services or the user experience. Ideally, if you want to get the best optimized solution, the most efficient processing, you can typically achieve that by putting the workflow where possible into a stored procedure into the database. And this may seem counterintuitive, right? Because what we're saying is that this whole video is talking about a workflow component in a service area called data in action. And where's our data? Well, it's in a database in data at rest. So is there some sort of disconnect here? What's going on? And the point is, there isn't really a disconnect because the boundary essentially is artificial. What we're really saying is, when we're building a workflow component, use the best technology, put it where it needs to be. So if the best way of implementing this particular workflow component is a T-SQL stored procedure, it's still logically a data in action workflow component. The deployment option that we've chosen for implementation is stored procedure in the database. And to a certain extent, that's also true for, let's say, an operating system service. So if I was using a Windows service on a Windows server, the question is, where does that Windows service exist? Does it exist on a server on-prem, in cloud, next to the database server, on the database server? No fixed rule, right? I mean, what you need to consider when you're looking at that particular Windows service is what makes most sense. Bear in mind that anytime data crosses a server boundary across a network, you have a performance issue. You have a security issue. So when you're looking at where do you put these Windows services, think about the security aspects, the performance aspects, the functionality that you're providing, and then make a common sense decision about where is the best place to put that Windows service. And again, as part of our enterprise architecture, we'll be doing some deep dives on how do we build Windows services, how do we deploy Windows services, and how do we decide where to put them. So given that we've built all of these nano services, how do we call them? So essentially, there are two basic mechanisms. Either the nano service is triggered, something happens that fires off some sort of event that says, do this workflow component now. So typically that's going to be users interacting through a user experience. It may be the fact that a record was updated in data at rest. It may be the arrival of messages or events from other systems. So something fires in, say, in Azure Event Hub, that's going to trigger a workflow component in Azure Functions to go to the database and update something. So triggering is where a lot of events essentially come into the environment and result in workflow components being executed. The other option obviously is now scheduling. So a scheduled event is something that happens every hour, every 5 minutes, every day, 3 times a week. And essentially, there are lots of different schedulers available. You don't have to build your own, right? So there are database service agents that run within the context of databases that would be a great place to put a workflow that is going to be implemented in stored procs. So if you've got a bunch of workflow components that need to be executed on a daily basis or every 5 minutes, then you know what, it makes sense to encode those as a stored procedure and use a database service agent to actually invoke that procedure at a given frequency. If we've got functionality that has to exist at the operating system layer, then great, we have operating system timers. So we can associate command files at the operating system level to say, well, okay, every hour run this command batch file that's going to go through and clean out all of the logs. And then the other option that we have here, obviously, is something like a polling background service. So, for example, if I've got something that I want to sort of like check my messages or check for an ETL once an hour, I might have a background service that's running, that's polling to see whether or not something has arrived. So this is sort of like a bit of a mismatch between something that's scheduled and something that's triggered. But a polling background service could be doing a scheduled lookup every hour, check to see if this has arrived. So let's have a look at how this might work in a code example. So here I've gone back to my functionality. I can look here and I can see I've got something called clear application state, and I can click clear application state, and in the background it's going to go and execute that command and refresh the page when it's done. So what happened? Well, essentially my user experience has detected the fact that I wanted to run a command, and it's now going to go to a REST API to execute that command for me. So let's have a look at what that workflow actually looks like. So when I selected that command in my user experience, control is being passed to this commands raiser component. So here I have a Telerik combo box, which is displaying my list of commands. And when a command has been selected, I'm going to execute action. So this is where the plug and play thing comes in. I am not executing a specific action that only will execute clear command. I have a generic component that will be executed on any form that potentially could display commands to a user, and it's always going to do the same thing. So in this particular case, it's going to check that the page is valid. Assuming that the page is valid, the first thing it's going to do is save the instance. It's going to save any data that potentially has been changed on that page since it was loaded. And then assuming that the changes were successfully saved, if there were any changes to save, it's going to come down here and it's going to execute the command. To execute the command, it's going to call a REST API. And the only information that we're going to give it is we're going to basically tell it the user session GUID and user GUID. We're going to tell it which command was selected and which instance we want to run that command on. 4 pieces of information. And those 4 pieces of information are completely generic. On any user experience form declared within Trellis Spark, we will always have the current user session GUID and user GUID. Those were set up when the account was signed in and the user entered the workspace. The current instance GUID represents the record that's currently being displayed, and we've just updated with save instance. And then the command GUID is the GUID that's associated with the command definition in that data model that we looked at earlier. So this is where the plug and play comes in. I can add any command anywhere in my user experience, and it's always going to go through these half dozen lines of code. It's always going to initially check, is the page I'm on valid? Save any changes on that page. Execute the command, please. And it does that by calling this call command. And then once the command has been successfully called, it's going to execute this line here, where we reload the page, because obviously execution of the command could have changed the state of the object, in which case new fields may be available or should be hidden. The state of the object may have changed. All sorts of other things can go on. So essentially what we're doing here is saying, great, page is good, save any changes, call execute, reload the page, please. Totally generic. Any object, any command in the user experience. So let's have a look at what's going on here. So if I go into call command, here's what's happening in call command. So call command is being set up. So call command is basically set up as a singleton service here. And you can see the call command functionality is very, very simple and straightforward. All it's going to do is take the command information that we gave it, so the user GUID, the session GUID, the current instance GUID, and the command GUID, and then it's going to call an asynchronous post against the command target. So here in the user experience, all the user experience is going to do is say, I just opened up this object. Based on the fact that this user has this roles, these are the commands that are available. The user clicked this command, and so all I have done is I have created a execute command information block with the user GUID, the session GUID, the instance GUID, and the command GUID, and then I have made a call to the REST API attached to this user interface to execute the command. So let's go and have a look at what that REST API looks like as an example. So on the REST API, we're going to come into this command controller, and it's essentially going to take the command information that it's been given. We're going to check that the model is good. We're going to connect to the underlying data at REST repository, and then we're going to call this function here called call command or event, and assuming that everything goes well, we're just going to return OK. So let's have a look at what call command or event is going to do. So here we have our call command or event. So the first thing it's going to do is lock the instance. So here you can see that we're using our session GUID and user GUID. So this is where our context, our user context comes in. We've passed that from the user experience into the REST API. REST API can now use that user context and the instance GUID that we've given it, and it can lock that record. So assuming that it gets the lock, now what we're going to do is read the latest version of that record. And this confirms that right now, this user context has access to the record that we're going to operate on. And if it doesn't have access, then we don't let them do anything, right? We're going to unlock it and we're going to go back and say, sorry, you don't have access to the record. But assuming that the user does have access to the record, then what we want to do is we want to see whether they have access to the command. All right, so what we're going to do is we're going to have a look down at the instance data that we got back and says, what does this user actually have access to this command right now? And when we pull the command data back with the command GUID, what we're going to get is this a SQL call or is this a REST API call? And in future extensions, we're going to be connecting directly to things like Azure Web Apps. We're going to be connecting to Logic Apps. We're going to be connecting to Azure Functions and so on. So essentially what we're saying is the user must be able to lock the instance. They must be able to read the instance. They must be able to pull the command data. And then depending on the command data, then we can figure out what to do next. So essentially we're initializing a bunch of information about the command here. And then we're deciding whether or not we have a command or we're going to call an event. And assuming that we're calling a command, then depending on whether it's a T-SQL or a web API, we're going to call the appropriate functionality. So we'll always call T-SQL first, and then if there's a web API, we'll call that second. So if there's no T-SQL but a web API, we just call the web API. If there's SQL but no web API, we just call the SQL. And if there's both, then we call both. So we validate that the command is good to go. We then decide whether we're calling T-SQL or a web API. If we're calling T-SQL, job's really simple. We're just going to execute the SQL command, giving it the user GUID, session GUID, instance GUID, and the name of the stored procedure we want to execute. And then we're just checking to see whether that T-SQL call was good or bad. And if it was bad, then we're logging an error. If it was good, then great. We're just logging the fact that the T-SQL call was successful. On the other hand, if we're deciding we're going to call a web API, then one of the other things that we do is we're going to look at the command target and figure out whether it's a local command or it's something that we need to call an external web API for. So essentially, when we set up our user experience is always pointing to the core Trellis Spark REST API. And that Trellis Spark REST API acts as a dispatcher for any custom APIs that you're going to put in place. And again, we're going to cover this in a lot more detail in other videos, but essentially, the process as a whole that I want you to get a feel for here is that none of this is dependent on the command that I'm actually trying to execute. All of this is generic framework, any command off any object at any time. And essentially what's happening is that we're bringing this command call from the user experience into a centralized REST API that can be called cross-platform. And then within that REST API, we're going to the data at rest, we're pulling the object information down, we're pulling down the information about the command, and then we're going to execute that specific command. And as a result of executing the command, we're going to say whether it passed or failed. We're going to add milestones to the object. There's a whole bunch of really nice stuff that we do in the background as well. But the idea here is that the whole process is generic. Right? Everything is plug and play. If I've got a user experience where I have an order of type A and it's got command process A, and then 6 months later I have a new order type called type B that says process B is the command, I don't need to modify any of this code. All of this code stays exactly the same. All I need to do is add a new workflow component called process B, which could be as simple as putting a T-SQL stored procedure in a database, or I might want to deploy a REST API or an Azure function or whatever else, and then all of my UX code, all of my REST API code has stayed the same. The only thing I have had to design, build, and test is the process B functionality. So let's consider the DevOps advantages of what I've just discussed. This whole process is highly compartmentalized. When I talk about deploying the process B workflow component, I might be talking about 5 lines of code, 10 lines of T-SQL. Maybe it's a small REST API that's going to be implemented in 20 lines of code, right? This is a small compartmentalized piece of code. The security model is already baked in because to even get here, I must have authenticated the user. I must have established a session GUID for that user. So I can make sure that I have implemented security on the component in exactly the same way as I've got security in my data at rest, because it's the data at rest that's validating that component's access to that data. If I try and read an instance that this user session does not have access to, it will fail from the data at rest. It also means that because this thing is so highly compartmentalized, that we can really focus on the quality of that 10 lines of code in the process B functionality. That means we can make sure that that code is really reliable. We test the hell out of 10 lines of code. It's easy to do that. And then the rest of the framework is responsible for figuring out, well, who can actually push the button to initiate process B. I don't need to worry about any of that. So the 90% of code I would normally have had to write to figure out who can push process B button is gone. That's dealt with. That's in the data model. That's in the user experience. That's in the dispatcher within the REST API. So all I need to focus on is the 10 lines of code that's actually going to do the work. So I can be really clinical about what does that code do? How am I going to test that code? How can it fail? How can I make that really robust so if it fails safe? And then the other part of that is the only thing that's going to fail is the workflow component itself. And if it fails, as long as I'm logging the fact that it failed and telling the user experience that it failed, everything else is already taken care of. So compartmentalizing to this extent gives us what we describe as these nano-services, right? It's this clinical, surgical, put the 10 lines of code in there to implement process order B and nothing else, put the data in there that says this user at this point in time can actually call process B. And then the other side of this then obviously is it's easy to test and integrate. Integration is essentially done. It's a non-issue. As long as you've put the data line in that says, well, at this point in time, this user can initiate process B, that's it. Integration done. It was the data. You put it in there, and the user now has a button on this screen that says process B. And the code that I need to implement process B is isolated and compartmentalized to that 10 lines of code. It's easy to test it. It's easy to integrate it. And then the other thing is, it's really easy now to horizontally scale it because you've met all of the criteria for a service-oriented architecture. Where your component is stateless, it's encapsulated, it's abstract, it's got a well-defined contract, okay? And it's dataless. So if I am going to do tens of thousands of process Bs per second, I might want to put that in a web API and then scale it and load balance it across 20 servers. And that's easy to do. So from a scalability perspective, being able to deploy these nano-service components means that we can then scale individually any of the components we decide we're going to deploy. Now, we talked about flattening hierarchies, but we also achieved reusability and composability as well, right? Because if every service, every function has got a common interface where we're giving it a user GUID, a session GUID, and an instance GUID, then it's really easy to compose things in the future, right? Because any service that we are deploying in this nano-service architecture is going to use those exact same 3 things, and they will have already been passed into the top of the hierarchy. So from that perspective, doing reuse of generic components within the hierarchy is almost a no-brainer. And as we've already said, right, if I have now deployed version 1 of process B, that was easy to deploy. It's this small thing, version 1, I'm just going to deploy it and I'm good, I'm done, right? I only need to test the fact that version 1 of process B was correctly deployed. I don't need to regression test the whole user experience and the whole application, which means that it's then very easy if I come along and say, you know what, version 2 of process B is required. There was a bug, there was a change, there was an enhancement. So I want to basically change from version 1 of process B to version 2 of process B. Well, this is now really easy, right? Because all I've got to do is either side by side process 1 and version 1 of process B and version 2 of process B, and keep them both going if I want to deploy multiple versions, or I can just do a straight replacement of process B with the new version of process B, and then everything else is going to pick up the new version. So this gives me some really simple DevOps to be able to deal with. And when I make a change into my code for process B, I never have to regression test everything else. It's all isolated into that one simple thing. So this has huge impacts on sustainability when you think about it. So first and foremost, from sustainability, right, we want to minimize the number of technologies. So you don't want 80 different IDEs, languages, libraries, etc. Okay, keep it down to a small number. But you'll never get it down to, well, it's just Microsoft or it's just Java or it's just Bit. There will always be some variation within a large organization around the different techniques and languages and technologies that you're using. There will always be variation, but minimize it. Because the more you minimize it, the more likely you are to be able to cross-train people, the more likely you are to be able to pull a developer off one project and move them onto another project. So to get the most efficient use of your human resources within the IT department, minimizing the number of technologies in use and standardizing their use makes it easy to move resources between projects and teams. One thing that you should focus on when we're considering architecture is most languages have an if statement, a for statement, a switch statement, exception handlers. The reality check today is that one language is pretty much as good as another. Whether you're using Java, C++, C#, VB, from a language perspective, you can pretty much do anything you want in any language. You may have some nice libraries over here in PHP, but the reality is you probably have just as good libraries in any other language as well. So what you need to look at when you've minimized your number of technologies and the number of libraries and the number of frameworks you're using is keep that as your minimum working set, but constantly monitor to see whether there is a better technology available. So if something significantly changes and enhances, then it makes sense to update your architecture to use the better technology. So to give you a practical example, a great idea is if we look back at 2019, everything we were building was in the .NET framework. We were using version 4.7.2, and we had an ASPX website, and it was good. I mean, it did everything it needed to do. It had a nice user experience, really efficient, very nice. Okay, but .NET Core 5 came along with WASM Blazor, and that was a better technology. And so we took the decision that we've got all of this dynamic page builder technology that we wrote in .NET Framework 4.7.2, but there are huge advantages to using .NET Core Blazor WASM technology instead. So we rewrote all of our dynamic page builders using the new Blazor WASM technology because it was a better technology, not because the market said, hey, look, there's this new nice thing around. Okay, there was actually a noticeable upgrade in doing it. We got times 10 performance improvement from a user experience perspective. The users are much happier. We got these brilliant WASM components that we were able to compartmentalize into class libraries, which meant all of our builds were better, meant our code reuse was better. There were real advantages from taking what was our legacy product that we'd been working with for over 10 years and totally rewriting that component to use a better technology. So there was a reason to upgrade, and that's what you should be looking for, right? You should be looking for a reason. So look for better technologies, and as they become available, and they will become available, then you want to update your enterprise architecture to take advantage of those. Now, another thing about this example that was really awesome when we did it, we were able to rewrite our entire web user experience from .NET 4 Framework 4.7.2 to .NET Core WASM Blazor, which is a completely different architecture, completely different way of building applications, and it didn't impact any of our existing clients. We could upgrade in place from here's how you render the page in .NET 4 to here's how you render the page using .NET Core 6 WASM. We didn't have to rewrite the data models. We didn't have to rewrite all of the REST APIs. We could just in place upgrade from one framework to another framework because we had encapsulated the user experience component, because we had basically written a dynamic page generator, and because we had abstracted all of the functionality for those applications into data in action and data in motion and data at rest components, we didn't have to worry about will we be changing any of the stuff that sat at the lower layers. All we replaced was a component in the data presentation layer from one to another, and all of the rest of it followed. Let's look at the other options here. So designing reusable components. We want to be able to drop these components in with a standard interface where they can reach out to get configuration data either from their own settings files or from the data at rest repository that then changes the way that they work. And again, if we can do that, if we can design these reusable components, then again, we can reduce significantly the amount of code that we're actually creating. And we talked a little bit about this idea of consistent, simple interfaces so that we can easily compose these solutions and keeping them small to make them easy to version and deploy. And this really does have an impact on sustainability, because if you meet these criteria that we've outlined here on this page here, then instead of having to write big monolithic applications or large services with encapsulated data, what we're down to in data in action is the 10 or 20 lines of code for process B. And that's it. It's just that simple. All of the rest of the surrounding code to decide whether or not this user can see process B has evaporated. We don't need to write it. So if we can figure out the most efficient way of writing the 10 lines of code for process B, if we can encapsulate that workflow component as its own deployable item and automate the test to make sure we maintain the quality as that code changes over time and drop it into a CI/CD pipeline, then we've reached the ultimate in terms of coding efficiency. The only code we wrote to support that function is the code associated with the function itself. And then because we can deploy that function as its own unit and scale it as necessary, we have also got to a point where we have a small infrastructure footprint. We aren't scaling big components that maybe there's only one or two operations that are used frequently. We're only scaling the small components that are used frequently. So the end story on sustainability is simply this. Small nano-services that are dataless within a data agnostic service environment improve the flexibility of your workforce, makes it easier to move people between different projects as required, makes it faster to develop and deploy new functionality within your environment, reduces the risk of deploying that new functionality within your environment, and makes it easy to maintain that functionality and ultimately replace it over time.
To learn more about Great Ideas products and solutions, visit greatideas.com. That's great ideas with a Z.com. Thanks.